Swayam Prabha. Digital India. Educated India.
Today would be talking about the use of heating and freezing methods as well as blasting methods in ground improvement. This is something that these three methods are not really usual, but then when there is a certain circumstances one needs to really use some of these things. What we discussed in the earlier classes was that suppose use preloading or use of prefabricated vertical drains. This results in changes in soil state because of the water content variations. So, these water content variations what we call was hydraulic modification methods is the way that we remove the water content so that it improves the strength of the soil or accelerates the consolidation of the soil. But then there could be some cases where you can also change the soil structure. So, for example, this soil structure is something that is a very the particular arrangement of soil including the way that the cementation bonds, there are many issues in soil structure the way it is defined. So, the water content changes could be one thing, but at the same time if you are able to change the soil structure whether by introducing some methods. So, we call them as some sort of what you call the temperature control methods, we call them as thermal modification methods. And you can also use some modifiers, many modifiers we would be discussing in the subsequent classes. We have a lot of modifiers here. So, we discuss how to improve change the soil structure so that it improves the overall performance in terms of the bearing capacity as well as settlements or even permeability. So, we would be talking about the methods based on temperature control, which we say it is a heat treatment method and ground freezing method. The heating methods are something that are very unique because you need to have some more information about the properties of the soil here. One is called the thermal conductivity of the soil. Actually, this is a very important parameter, and heat capacity of the soil, heat of fusion, heat of vaporization. These are all some terms that influence the method itself and also the way that you control the temperature. We would like to see the definitions of some of these terms. One is basically what is the thermal conductivity of the soil. It is actually the amount of heat passing through one unit of the cross sectional area of the soil under a unit temperature gradient. So, you have a temperature difference T2 minus T1 is a temperature gradients, and the length of the sample is say 1 meter or whatever, area of cross section is there, and then the Q is a heat flow in watts and area of cross section. So, you will get what is called the thermal conductivity of the soil, and this is a very important parameter, and by the definition of the term itself one can make out that one can determine the property of this KT in a laboratory in a simple manner. What you have to do is that you have to find out the heat flow and introduce some temperature gradients, and then you have a length of the sample, area of cross section of the sample is known. So, you will be able to get KT value, and this is in fact a function of the temperature, and at 0 degree centigrade for water it could be 0.58 watts, and actually this is expressed in terms of the watts per meter per Kelvin, and for ice it is 2.2. So, you can see that for ice it is much higher, and then for denser frozen sand this is a typical value. Say for example, somebody has observed in literature KT value would be about 4 units, and in the unfrozen state it is less, as similar to that. So, in the case of ice it is 2.2 and it is less in the case of when it becomes water like 2.2, and then there is a difference, a good difference. Similarly, you have a dense frozen sand, you have about 4 units, and then when it is not frozen you have a lesser value. because this thermal conductivity, like once you heat the soil, what happens is that water content is removed, and then the stiffness increases, the strength increases, there are so many properties that you get. And for soils, thermal conductivity increases with water content and dry density. This is an important factor that we should understand, that higher is the water content, higher is the thermal conductivity. Water is there, so water, because of the presence of water, there is an increase in the thermal conductivity, and also the dry density. The particles come closer to each other when the soil is dense, and you have a better thermal conductivity. The term heat capacity of the soil is another term that we should understand. It is the amount of heat required to raise the temperature by 1 degree centigrade or 1 degree Kelvin. It is expressed in terms of the unit volume, like you can say volumetric heat capacity, or per unit mass. Either we call it specific heat capacity. This is the equation, Q is C m delta T. So, normally we can say what is the heat capacity of the water. It is actually, heat capacity is, for say for example water, it is 4.2 kilojoules per kg per degree centigrade, and you can see that it is about 4.2, we can say million joules we call it, per meter cube. So, 1 meter cube of water has if you want to raise it by 1 degree centigrade, you have this much of energy spent. Okay, so you can see that. So, even for ice, if you want to for the ice also, you have this much of temperature. This is another property that we should see. So, the heat capacity of the ice is less than that of water, this one should understand. There is another term that people use, it is called latent heat of fusion. All materials have some sort of internal energy, and whatever is the thermal energy. In this case, it is a change in the thermal energy when the water freezes or ice melts, water freezes or ice melts. It is about 334 million joules per meter cube of water, and to melt one mass of some mass of ice, the heat quantity, sorry, this spell Q is LFM, and for a meter cube of soil with water content, you have this 334 units into dry density and water content. So, there is another term that we have, which is called heat of vaporization of water. It is energy required to boil water from liquid state to gaseous state, and at atmospheric conditions we say that the heat of vaporization of water, like you see that the when water is getting heated, there is a vapor pressure. So, that latent heat is in terms of 20 to 60 million joules per meter cube. So, as a simple example, to remove all the free water at 100 degree centigrade in 1 meter cube of soil with water content W, the amount of energy required is LVS, where it is equal to 20 to 60 rho d, means the density of the soil and the water content. See, the thing is, some of the definitions are quite useful, because they will give some information about the thermal properties of soils. But one should understand, like say for example, the ground temperature is minus 10 degrees, and you would like to make it to 10 degrees, minus 10 to plus 10 degrees centigrade. You will be able to get some sort of information here, what is the energy required. Essentially, why these calculations are required is that the property of the soil, the other input parameters, you will have a rough idea of what could be the basis on which one can calculate the required energy. Say for example, we have a situation where the material is to be heated. When the material is to be heated, what is the amount you have to, energy you have to give in, one must calculate. So, to that extent all these definitions are important, otherwise the design will not be complete. So, using all these terms, one can design some sort of heat supplying system or even heat recovery system. Say for example, you would like to take heat from the soil. So, you may have some other way of doing it. So both are possible, whether you can supply heat to the soil, so that it becomes very stiff. Say for example, when the temperature water is removed, What happens is that when this soil is heated to a very high temperature, say for example 400 degrees centigrade, that is what in the olden days people are using the burning of bricks is a classical example. You are trying to use this temperature to bring all the particles together, make a very good soil structure, so that they are very strong. You know, the in situ strength of the intact strength of the brick is going to be very high because of the heating. What in what way it helps? It brings the particles together, and because and then the water is also removed. So that means it is going to be very stiff, and the stiffness values are going to be very good, like so the settlements are going to be less and all that. So these definitions one should make use. How do you go about treating the soil? Actually this is a very important concept here. So for example, as I just mentioned, there could be even mineralogical changes that could take place when higher temperatures. One should check it up, particularly if say for example, if there is a halloysite mineral present, definitely it could there will be significant changes in water content. In fact, I was testing the soil from Cochin area, which soils from Cochin area are very soft. What happens is that you take that soil and then keep it in the atmosphere for some time, you can find out its liquid limit in natural state. The moment you bring that natural soil, putting it in the plastic covers and tie it and then bring it to the sample and then find out its liquid limit, you will get some water content. But then you take the same amount of same amount of soil and keep it for air drying, and then because of the air drying, air drying means essentially you are subjecting it to ambient temperatures, like say for example whatever exists here, either it is in Bangalore or Kerala. What happens, because of the ambient temperature, again the soil particles will come together, and then the soil particles come together and then they become much more stiffer. The whole soil structure becomes much more stiffer, and in fact in one case I was able to see that say for example the initial